Thank you for joining everybody. Today we're going to talk about how to design for plastic welding, laser plastic welding. Quick agenda here, we're going to talk about answers to your questions. So the way we do these webinars is we want them to be interactive and engaging. So as the questions come to your brain, please type them in the chat and we will do our best to answer them as we go. We don't want you to hold those to the end. We want you to get those questions out right away. We're going to talk through the basics of laser plastic welding and the different types of plastic welding. We'll talk about absorptivity, transmissivity, and how to design your laser welding joints. And then, of course, we'll talk about best materials. Our presenters today are
Catherine Urives, sales engineer. My background is in our applications lab, so I've got my hands on many laser welding opportunities and projects. So I guess that's kind of where my credibility in talking here comes from. And then
my name is Nick Flesher. I'm the director of innovations and technologies here. I am our laser plastic welding business unit manager. Work with our quoting department, applications lab, and I've been with Extol for about 14 years. So excited to talk to you guys. Can't emphasize enough Jason's points on questions. A lot of times these webinars will turn into almost like a brainstorming session for your specific parts. So we love that specific of a question. If you might stump us. If you do, we're going to say it. We're not going to make it up. That's for sure. Yeah. So with that,
AI.
We are not. That's true. Jason, are we good to start?
Yeah, we're good to start.
All right.
Take it away.
Great. See if my clicker will work.
Well, the suspense was there.
Yeah, we'd love to know, use that chat, why you joined this webinar. We've got everyone muted, so you can't scream it out into the abyss. Let us know in the chat. We'd love to know why you joined. I think that might actually help us very real time adjust our webinar to your needs. Yeah. So if you want to just do that while we get going, we find it's useful to be able to say, or for you to be able to know who you're presenting, who's the company that is presenting to us. Mm-hmm. We like to solve complex plastic manufacturing challenges, typically in the joining or the welding or the staking, riveting phase, but many challenges is something that we see across customers. And we find that there's kind of a spectrum. Plastic welding expertise in companies that specifically do welding. Then there's kind of the other side of the spectrum, which is custom automation experience. And we find that sometimes custom machine builders might lack plastic welding experience. Extol is always striving to be the best of both. We want to make sure that the equipment that matches the technology, we sort of see them hand in hand, and we have experience in both those things for decades. We're actually 40 years old this year. And so from that custom machine background, we make sure that we match the plastic welding expertise to that. Just to kind of give you an overview of the services we offer. Again, we're going to get into the content here in just a minute. We offer engineering services. We do some 3D printing with some HP multi-jet fusion printer, so a little bit more of a high-end printer. We do part development with you, specific. If you don't know how to design for a weld joint, we have a whole department that does that work. We can make prototype parts, pre-production parts, kind of small-scale production validation. The plastics assembly technology piece that we offer, we have different welding technologies. Laser welding is not the only thing that we do. So if there's a better technology suited for your problem, we make sure to offer that up. Laser welding is not for everybody. InfraGuide's a proprietary technology that we have that is sort of heating both parts at the same time and then pressing them together. Hot plate welding, same kind of concept, but with heat plates that the plastic may touch off. Spin welding, a frictional process. InfraWeld is sort of a through transmission. It's like a spot weld. Ultrasonic, we don't make our own ultrasonic equipment, but we offer a variety of different suppliers in our custom solutions. And then our riveting technologies, InfraStake and NanoStake. Those are proprietary to Extol. It's our own product. And then from an equipment side of things and how those technologies are implemented, we have fully automated systems, semi-automated systems, which have some operator interface, standalone or some cases standard equipment that we literally have an inventory of, or integration. If you've got a machine builder of choice, we sell all of these technologies that you see in the middle there to those machine builders. So that's in a nutshell. Catherine, if you want to talk through I have a little bit of a delay here. Yeah.
Oh,
okay.
There we go.
Great. You want to talk through the laser welding process a little?
Yeah, for sure. It looks like there's even a couple people who have joined the webinar specifically to learn the basics, which is what we're just about to run through. It looks like we've got some other people here who just want to learn the main use cases for laser welding. Great reason to join. Bill wants to laser weld and seal a container that is also snap fit. Sounds like a very interesting application.
I've seen that before.
Both
Yep.
and.
Yes.
Interesting.
Both and.
Cool.
Yep.
Well, I guess then here, let's just start at 1,000-foot view what laser plastic welding is. So on the far left side of the image, hopefully it's showing up on the left side of your screen because that's where it is on mine, but you have two components. You've got that top component that is represented by, you can see through it, it's transmissive to the laser wavelength. And then you've got the lower component. These two components are clamped together. So there's force applied to the top component that is then transferred into the lower component. The next key piece is heat. Pressure and heat is what makes a good chemical bond. So we've got the laser that comes in and traces the weld profile of your specific part geometry. There is no standard shape that you need your part to fit. The laser path is programmed to your specific application. Once the laser passes over the part geometry for either a set number of times, a set amount of distance, anything like that, those are some kind of more in-depth parameters that we can discuss. Then the parts are held in a cool phase. You need to cool that molten material down before you can remove the pressure of or the force of the press from the parts, and that's how you get a good, strong chemical bond between the components. So that's laser welding. Fairly simple up until this point. Key elements for laser welding. Like I mentioned, you need intimate contact between those two components. If the components are not touching each other, you can heat the parts all you want, and you're not going to get a bond. I mean, I picture something like pretty dramatic, but like a potato chip on a flat piece of plastic. If they're not touching, how are you going to expect there to be any welding that occurs? So you need intimate contact between the two components. That's where the clamp force comes in. Next, this is a pretty cool graphic, so keep your eyes open for this. Here, you want me to run it again so you can make your sound this time? Ready? And... So what you can see there is that the laser comes... Let me turn on my little laser pointer. I knew I was going to want to use this. So the laser comes in... Oh, I thought I could draw a line here. Is it showing up as a line?
It's not.
Oh, no, you can't. It doesn't let you draw. It just...
Man, it was going to be so...
move it.
It was going to be so much cooler. But okay, so the laser comes in and it transmits through the top component and then absorbs into the lower component. So you can see this little red bit here is where the laser energy is actually being absorbed. So the transmissive component and the absorptive component are key elements for laser welding. We get my laser pointer turned off. And then lastly, you need compatible materials. This means at a chemical level, the materials, when heated, can bond together and create a strong hermetically sealed joint. You can, and I'm going to put can and maybe some quotation marks, emphasize, italics, all that stuff. You can technically combine, I'm not going to say weld, combine dissimilar materials. However, it will not be a strong joint. So if you've got questions just generally about different resins out there and their compatibility to each other, on the Extol website, we've got a material compatibility chart that you can reference. I'm sure Jason can get it sent out as well after the webinar. That's a huge resource that we see people download from our website. So that's free for you to view and then utilize as you need. One thing I will say about that quickly is the material compatibility chart speaks generally about plastics and their compatibility. We always will recommend testing your specific material resin because underneath the PCABS umbrella, there's going to be so many different blends and variations. So we always get the warm fuzzies from being able to try your specific resin, and that's something we can do in-house.
I would also say transmissivity and absorptivity are kind of the same. There might be variations among the resins. but it's always nice to understand the boundaries of how much transmissibility at the specific wave. We'll talk wavelengths in just a moment. But anytime we can test samples sort of complementary, if it doesn't require tooling, we advise customers to do so.
Mm-hmm. Yeah, and a lot of resin suppliers will be able to send just material chips, and that's really all we need.
Yep.
It just gives us the quick, yes, we can pass through the top layer, the bottom layer can absorb, and so then it gives everyone the confidence moving forward into molding those materials and the laser welding process in general.
And can inform cycle time.
Yeah,
because that's always a key parameter.
Mm-hmm. I'm curious if anyone has used this material testing offering that Extol has in our applications lab. Has anyone maybe sent in a unique material and gotten us to weld samples up? I'd be curious to just know if we've got kind of repeat names and companies' projects coming into this webinar today or not, or we welcome your materials and projects that you've got coming to us in the future. So here are a couple example videos. I'm going to play this one on the left here first. So you can see this is a 2-cavity nest, and then the upper component was placed on the lower. As you can tell, this material is kind of a ghostly hue. It is still transmissive to the laser. So this purple dot dancing around the screen here, that is the laser tracing the path of the part. It is doing multiple fast passes of the part to uniformly heat the material and get a uniform collapse of the two components on top of each other.
I should point out, it kind of looks like it's jumping around, but that's really just because the frame rate of the camera is not able to capture how quickly that laser beam is actually moving.
Mm-hmm. Yeah, what do we do for this process? It was maybe moving 2,000 millimeters a second?
Yeah, we go anywhere from, in some cases, 500 millimeters, that's pretty slow per second, up to 5,000 millimeters per second. We usually start around to 2,500. I see a question, can both materials be the same, similar? Does laser transmit through the top and focus on the joint? That's exactly right, Wes. Mm-hmm. We oftentimes see, and in that case, the video you just saw, one was natural, that was nylon. Mm-hmm. I think that particular example was unfilled. We can do filled, but the thickness, we'll talk more about this in the design portion in a moment, but both of those were a nylon, I think a PA6 in that case.
Correct, yep. Here is a more automated laser welding cell that we did. What you're seeing here is 2 laser welders, and then the robots are loading laser welders as well as loading leak testers.
They're loading parts that aren't there.
Yes. Yeah. Imagining parts.
And maybe we're protecting some customer part data here in this video, but so you're going to see that the dial is going to turn into the laser welder. The unique thing here that I want you to notice is we've got 2 laser sources on this part. The last one had 1 laser source that was just going around both parts. This has 2 laser sources simultaneously tracing the part.
Why would we do that?
That is a fantastic question, Nick. I know someone was thinking that in the chat as well. The reason we would do that, golly, there's a couple reasons. I'll go for the big ones.
Okay.
The reason for this application was cycle time. We prototyped this part, feasible and everything, with a 1-source laser, but the cycle time was, it was in the 30-40 seconds.
Oh, no, it was 14.
No, for the prototype.
Oh, yes,
Yeah.
that's right.
For the prototype was about 40 seconds. Oh, you spoiled mine.
And we cut it.
Yeah.
And everyone was so happy about it too.
Yeah.
But the point being, when you add the second laser source, although it was feasible with 1, the cycle time went down to 14 seconds, from 40 to 14. So, and I'm kind of prematurely stealing Nick's thunder for a later slide, but this kind of goes to the point that our goal is to help you configure the equipment so it fits your application. We may be able to do it with 1, but to hit that cycle time, we would have had to have how many laser welders in this system? Or you put 2 sources in 1 laser welder, and then it goes faster. So
we've got a question. Do you need an energy director in your part, or can it just be flat? Excellent question. Mm-hmm. It can just be flat. We do like to see a sacrificial rib. We'll talk depths here in just a moment, some details on that, but a flat to flat is no problem. That said, it's not uncommon. This is probably, I don't know what percentage this happens. It's not like 50%, but I would say like 10 to 20% of the time customers have designed for ultrasonic, and maybe they're damaging some components, or maybe they have some A surface read through. We can clamp just enough to start the weld process. even with if you're not familiar with ultrasonic welding, you have to have like a little triangle to start the weld process. We can't even do energy directors with laser welding, but most of the time, in fact, we recommend anywhere between a 0.5 to 2.5 millimeter weld rib width. We can do wider. We can do our laser path can actually be up to 25 millimeters wide.
That's a big beam spot.
We can do
that large.
And we can do flat to flat, but we don't recommend it.
Yeah, there's some part
CeeLo
variation issues that come into play.
You need force. I mean, Catherine said you need force. What you actually need is pressure. And so having a sacrificial rib allows you to get more pressure into the weld joint with less force.
Mm-hmm. Listen, Jason, I know you've been itching to present this slide, so I'll give the floor for just
some reason,
one.
people at Extol are scared of this slide.
You're calling me out right now.
So this is the electromagnetic spectrum. This is not something that we created. It's, this is like laws of physics kind of thing.
It's science, Jason.
It's science. So the electromagnetic spectrum accounts for like the visible wavelengths that we see when we see color. Those are different wavelengths that our eyes are perceiving. On one end, as wavelengths get shorter and shorter and shorter, we're in the gamma rays and X-rays and the harmful UV, the ultraviolet rays that we get from the sun that can cause a skin tan, but it also can give you a sunburn or cancer. Then you go to infrared. That's just on the we just can't see, the human eyes can't perceive infrared wavelengths. And it also has these heating properties. So as you zoom in on the infrared portion of this electromagnetic spectrum, we have what we call near IR on the left. And as wavelengths get even longer and longer and longer, we get long wavelength IR. We show this because plastic responds to different wavelengths of IR energy. And so we'll talk about 1 micron and 2 micron. Really, they're not exactly, most lasers aren't exactly 1 micron. The near IR wavelength that we use is actually 980?
Yeah, 980.
980 nanometers. And you can see on the screen here, there's a couple other wavelengths that are right around 1 micron. But we're using 980 on ours. And then over on the right-hand side, in the short wavelength IR is 2,000 nanometers. And is that actually 2,000? Do we actually use the 2,000?
I think it's 1940.
1940 is what we use.
Yep.
And then if you're familiar with Extol's InfraStake product or even our InfraGuide product, that is using a bulb, and that's more like IR welding. That emits a spectrum of IR wavelengths, whereas laser uses a very specific wavelength. The laser source is generating 980 nanometers, that's it. And so when a laser turns on, we can't see it. The camera can see it in some of those videos because the camera is picking up some of the IR light, but our human eyes can't see it when you see it in person. So I like to nerd on this slide. It's my favorite slide.
Yeah, thank you for being a nerd for us all today, Jason. Much appreciated.
David has a question. What is the max thickness the upper material can have without impacting the weld transmissibility, using, as an example, polypropylene?
That's a great question. Nick?
I knew you were going to look my way. The answer, my favorite answer is it depends. It depends because kind of a more challenging application might be, say, a 30%. You asked about polypropylene, David. I'll use a little more aggressive of an example. A glass filled, like a 30% glass filled PA 66, 2.5 millimeters is going to be about the limit. Polypropylene, what's the colorant? Jason kind of talked about the IR spectrum a little bit. 1 micron cares about the absorptive properties of the plastic, and so it's this combination of how much power do you need into the weld, what's the weld rib thickness, right? If it's a smaller, think in terms of pressure, except with the energy. If it's a very small beam spot, and we can adjust that because the weld rib is small, then it can actually penetrate just a little bit deeper. I would say how much absorptive material is in the lower. And so at Extol, we kind of evaluate, all right, well, what's the weld rib look like? What's the transmissive properties? And what's the absorptive properties? In the automotive lighting or in the commercial lighting space, that we see a lot of acrylic, PMMA, and those can actually transmit many millimeters, even inches, if you capture the light correctly. And so then the problem shifts from transmissive properties to, can I get the energy where it needs to be? And quasi-sun, well, we'll talk into that a little bit more. Great question. I would say, let us help you. It's so specific to all those things that I just said that we really would like to understand your application a little better to give a good question to that. Mm-hmm. Maybe a question for later on the pros and cons of laser welding versus ultrasonic welding. Currently working on application. I love it, Gary. We're going to get to that in, I think, 3 slides. So we'll park on that. We'll make sure we answer that. Mm-hmm. Both those questions we'll give some more context to. Am I up? No, Catherine's up. Hand them up, phone back to you. I have a tendency to.
I gave you the question and then you just wanted to keep rolling, and I respect it. All right. So up until this point, this kind of image on the left here should look, very familiar to what we've been talking about here. You've got a transmissive upper component and an absorptive lower component. This is 1 micron laser welding. Now to just kind of give you like an absolute mind blow right now, there's also kind of 2 different approaches to laser welding. There is what's called 2 micron, which utilizes the 2 micron laser energy, the 1940 nanometer wavelength for clear to clear applications. You do not need to have one component be transmissive and one absorptive. I will say that there are some more limitations on clear to clear laser welding. For example, you need the material to be very, very rigid. Polypropylene with 2 micron kind of turns into, would pudding be a good description for polypropylene?
Yeah, it just heats differently.
Yeah, it like holds too much of the heat and then just kind of squishes.
Yeah, the question isn't really weldability at that point. It's, do you have heat effect that you don't want?
Correct.
Because you can see that.
Yeah, so you can see in this little picture here in the middle, let me get my laser pointer back on. So with the 1 micron, you can see that the heat is very concentrated right at the weld rib. That is ideal. It gives you a very forgiving process window, but also a very robust welding process. So for the clear to clear application, when the beam comes through, you can't choose where in the part geometry the laser energy is absorbed. So the farther you go down into the part, the more laser energy is kind of dissipated or lost. So when you get a material like polypropylene that has a lot less structure, this isn't necessarily a great option. I think typically we see most success with very rigid plastics like PC. I think PMMA is another one. But anyways, just wanted to kind of open the horizon up to share that clear to clear is a possibility with laser welding. People often believe that it's not. So then even further, when you say laser welding to people, they say transmissive and absorptive. If I can't make my component transmissive and absorptive, laser welding is not for me. False. We have another approach called direct laser welding. So this is kind of as it sounds. Instead of the laser passing through one component into another, both parts have their weld profile splayed open to the laser source. The laser will then trace both weld profiles for a certain number of passes until a certain amount of melt has been reached, and then the press will rotate and smash the parts together. It's basically non-contact heat and smash, using the laser to direct that energy. There are other non-contact welding processes. There's IR welding. There's hover, like hot plate hover. The reason that you would use direct laser welding is maybe due to some tight part geometry where you can't get access to certain features, things like that. But just wanted to kind of open up your minds a little bit more to the different ways that laser can be configured, because I think people think very one way with laser welding. Mm-hmm. If I can't make a component transmissive, I'm not using it. So just a little bit more in-depth information in, oh my goodness, into your options there. Okay. Every time I turn on the laser pointer, it gives me issues. So up until this point, Extol, the laser welding approach that we use, is called quasi-simultaneous. So what this means is that the laser traces multiple fast passes around the part geometry. This allows for the parts to be evenly heated and evenly collapse into each other. We find that this is the most robust welding process because, like I just said, you're evenly heating the part. You're not introducing part stresses by heating all the way on this side of the part and then smashing the other end of the part into itself later on. So that's quasi-simultaneous. And then there's also contour welding. This is also very common in laser welding. It is one slow, continuous path along the laser profile. So this typically used for some larger applications. Quasi-simultaneous is mostly utilized in when parts are less than 16 inches by 16 inches. That's kind of the limitation window for quasi-simultaneous. You can stack multiple sources on top of each other to open up that window a bit more. But generally, I'd say if parts are smaller than 16 by 16, we go quasi-simultaneous. Contours for something larger.
Yeah, and Catherine stated we have used multiple lasers and scanners for quasi-simultaneous on larger parts, but I would say well over 90% is sort of within that 16 by 16 inch window.
Looks like we got a question about enclosure requirements, but Nick, it looks like maybe you typed a message here in the chat.
Yeah, just generally speaking, you do need to there is a safety component to laser, and we have seen we've seen applications where people haven't taken the proper precautions for that. The most straightforward way is to have it was a great question, a light tight box. Things need to be light tight, and so you really need to have a certified laser safety officer evaluate that. We have a couple on staff. And then you really need to submit that to the FDA. This is kind of weird, but the FDA in the US anyway, sees more laser applications than anything because of how the healthcare industry. And so that's the government agency that sort of does that. And we have to do an annual review of every system that we sell. So there are regulations around this. There are some edge cases where you don't have to have light tight, but you have to, we follow what's called a 3 bounce rule. So that if the light isn't fully enclosed in a light tight box, we have to do all the calculations to ensure that light bounces 3 times. The reason that's a safe condition is because it's not focused any longer. So with laser welding, the focus is really, really important. And if you don't have focus energy, then 200 watts, 300 watts, 400 watts isn't as harmful.
Another common type of laser welding is masking. So this can be done, I'd say typically with quasi-simultaneous, where if the beam spot cannot be small enough, just due to very tight part geometry, a mask is introduced to kind of limit the beam spot size. So this would be, ultra precise. We're talking less than 0.7 millimeters is what you're looking for your weld rip width or your beam spot size. Not overly common, but an option. Mm-hmm. And then lastly, simultaneous. This is another big one in the laser welding world. So what this is individual fiber optics placed all the way around your part geometry that are simultaneously, rather than one beam spot turning on and tracing the part, simultaneously blasting the part with laser. So this is super fast, typically used with some large, complex paths, mm-hmm. a lot of intricate curvature. Maybe think of a automotive headlamp or tail lamp, something that's got a lot of geometry in every direction to it. Simultaneous is often used for that type of industry.
What's a typical laser weld width?
I would say we see anywhere, it's application specific. Like I'm thinking of in the medical space, microfluidics is kind of a large, sounds very specific, but it's actually sort of broad category. We may see beams in the 0.7 to 1 millimeter mm-hmm. Range, 30 thou-ish, all the way up to, I would say, 3 millimeters. And it all depends on strength. What's your application? Does it need to be ultra strong, or do you want it super aesthetically pleasing? Look at the slide we're on. We'll talk about that in a second. Mm-hmm. We've done up to a 1/4 inch wide because the application warranted it. It was a very strong, it needed a very strong weld. That weld took a while. If you just think in terms of how much energy you have every time you double the radius of the beam spot, it's round. It's a little round beam spot. And so it's a balance of how much wattage do I have, what cycle time do I have, what strength do you need, what aesthetics do you need? That's kind of that question. How does beam angle from a galvo scanner affect a weld and joint design. That is a deep question. I love it. I'm here for it. We typically use what's called an F theta lens on the Galvo, and the F theta lens essentially moves that beam spot from a small, I think it's 50 millimeter aperture, outboard to whatever F theta we choose. And so the wider out you get, if you think of like a flashlight projected on a bit of an angle, you can get a little bit of an oval on that laser beam spot. But we typically accommodate for that. So we do that in power, in the focus that we dial in. So we do, Jeffrey's sort of bring up, I guess, a little bit of an adjacent question, which is, how do we evaluate that? We basically trace the laser and we do the optical work and we make sure that's laid out and we give that to you in a feasibility report. So if you've got sort of a proud protruding feature, we call it shadowing. Most of the industry calls it shadowing. So you have to make sure you're not going to cast a shadow from that protrusion to the weld rope. So excellent question. Your joint design, you want to try to stay away from that. We've accommodated that with multiple scanners and sources. We've accommodated it with mirrors. We don't have much in this webinar for mirrors, but we absolutely have used mirrors, and we make sure that that's optically engineered to hit the weld bead, so or weld rib. So, great question.
And someone else just asked a question. Do different laser welding types, transmissive, clear to clear, etc., affect the weld strength? Yes, as well as the part geometry that goes along with each of those different types. So each of them, I'd say, have a slightly different recommendation for what the joint would look like. So if you've got a specific application that you're considering for one or maybe all three of those different types of laser welding, we can follow up with you and figure out specifically what joint requirements would be most helpful to implement into your design to reach your criteria.
What I would say is direct laser. Catherine talked about direct laser, and we've used that in some pretty unique situations. Like we had a customer come to us who designed it for ultrasonic, quoted it, won the work, and then ultrasonic folks said, hey, you can't do that because of far field welding. I'm not going to go into what that is, but they couldn't ultrasonically weld it. So they came to us and they said, we can't use a frictional welding process like vibration. It was nylon, and they said we need help, and we used this methodology. Their strength wasn't terribly high. Like it was in the, you're basically sort of heating the part really, really high, really, really fast, and it's oxidizing, and so you lose some strength. Whereas transmissive, 1 micron, the parts are in really intimate contact, and oxygen can't get to those parts and oxidize and degrade the material. It's actually conducting up into the upper layer. So those typically are at 80 to 90% parent material, if you're familiar with that term. So, in 1 micron, usually strength isn't the problem. It's more around, are we matching the aesthetics? You get more heat affected zones. So are you getting, an aesthetic that you want versus strength? Usually 2 micron strength isn't an issue. Yeah.
So laser welding benefits, just to close up this slide here, it's clean, meaning there's no particulate generated, which is why it's been such a popular thing in the medical space. Like Nick mentioned, a lot of lasers going through FDA approval. And then also like automotive or things where you don't want little bits of plastic floating around on the interior of your part. It is also super precise. We talked about the precision of the beam spot. This piece, I feel like, doesn't quite show the scale of the capabilities for laser welding, but this picture in the middle, the part that we're welding is like the size of an eraser on the top of a pencil. So it can handle a wide variety of applications. And then it's super fast. And I'm so happy to be getting off this slide because, man, that little purple circle was making me dizzy.
I was just about to say, that's like kind of speaks to what Gary had asked about earlier around how do you know if it's ultrasonic or if it's laser? It's typically cleanliness. That's probably the most common thing we see. Ultrasonic does a pretty good job, but there are times when, you can't chance any dust whatsoever. And so cleanliness is probably the biggest thing that we see. Precision is probably next. That energy goes nowhere else except for where you want it to go. If you've done ultrasonic welding before, it can kind of run away from you in certain applications. And so those are the two biggest indicators. Speed-wise, you're probably not going to actually beat ultrasonics for speed, but it's pretty darn close. I mean, that really small device that Catherine showed, I think that laser, that energy on time was 1 second, and the depth was 0.2 millimeters. So, yeah, that's probably the big. It's a more expensive technology than ultrasonic, but when you need it for those two reasons, you need it.
Strength of ultrasonics to laser generally?
I would say comparable.
Okay.
Yeah. I mean, it depends on fillers and all those kinds of things, but we typically say design for 70 to 90% parent material strength.
Nick, do you want to talk a bit more about the design?
Yeah, definitely. Well, you've got a link right here. Go, head over to our website. I'm not going to be offended. Catherine's not going to be offended. You can do it right now if you want.
Jason, will you be offended?
If they download those design guidelines and leave the webinar, then I'll be offended.
Yeah, that would hurt my feelings. So some of the slides you're going to see are in that guideline. It's general. We're trying to sort of hit this broad, all industries, as many applications as we can. But that's kind of what we're going to get into right now. We've talked about some of these things already, just answering questions. So if it's, I'll try to breeze through some of them. The transmissive part, it's got to be transparent or translucent to IR, but it doesn't have to look like it. We've got multiple applications out there where it looks opaque to the human eye. We've got an inspection system, so we can kind of check that out. But that transmissive part, we've shown some examples, natural, like you might be saying to yourself, well, I can't have a white looking part on a black part. It doesn't have to be that way. The most common example that we sort of give, and we didn't provide these systems, but most everyone is familiar with Apple's AirPods. Those are laser plastic welding. White on white is kind of the most challenging application because they can discolor, but that's just an example of challenging your norm of, well, it has to be clear to black, not necessarily. A transmissive part, semi-crystalline, we just roughly say 3 millimeters thick or less. I talked about fillers. If you're using talc or if you're using glass, we really suggest 3 millimeters or less if you can, especially if you need a strong part. Everybody's needs are different. We've had a couple strength questions. We see folks that say, I don't care about strength. It's a stitch weld. I just need it to stay in together or assembled until it gets assembled into a larger piece. And other customers say, it's got to be 100% hermetically sealed, crazy leak check requirements. We'll help you design for that. Amorphous plastics, and if you're not sure what those are, I encourage you to go out there and check it out online. We're not going to state which is amorphous and semi-crystalline unless I quiz Catherine right now, and that would be unkind of me. I would as well.
It's ingrained deep in my soul that the pressure of needing to answer on the spot could make me vomit.
I couldn't. Much thicker if it's transparent, right? Amorphous plastics just transmit and absorb a little bit better. Looks like we've only got 5 minutes, so we'll try to move along here. That glass filler sort of affects that quite a bit. We mentioned typically 2 millimeters wide. We see smaller. We definitely see wider. Plan for some interference. As I mentioned, and I would say this is not the norm, 0.2 millimeters is kind of the minimum though. We've done 1.5 millimeters, but just to give you an idea of range, that's typical. This technology is a bit different. You're not going to do like a vibration weld joint, if you're familiar with vibration, and displace 7 millimeters of plastic. It's not going to do that. So just kind of keep that in mind as a general guideline. We're just going to show some examples of joints. These are lap joints, simple lap joint, sacrificial rib actually can be a little bit of a conceal of your flash. Inline lap joints can give you a really clean aesthetic look. T-joints, you've got some parts that are parallel to one another. A simple T-joint is not fancy, but you might have no technology is flash free. You're going to have some amount of flash, but as you kind of saw from those images, it can be really almost imperceivable to someone who is not familiar. Sacrificial weld rib, this provides a really clean joint. You're going to have more flash in the absorptive material typically because that's where the energy is going first. then it's conducting to the upper. So usually we see more flash on the absorptive material. Lower skirt T-joint, this actually we see quite often for highly aesthetic. A lot of, I'm thinking in terms of like lighting applications, we'll see that. Upper skirt T-joint, that's kind of you need to locate a lid or high automation. Like if you're running, 7 figures of parts, like millions of parts, that's something to sort of think about. Radial weld joint designs. This is, you could do this by rotating the part. We find it's more cost effective really to still use a galvo and use a mirror. And you can bounce the part around and come in perpendicular to the part. We've helped customers design sort of a taper joint, 45 to 85 degrees. We like 45 degrees if you can get away with it. And then your part interference. This is probably the trickiest thing with this weld joint in a radial sort of joint. You need the interference, and you're going to have to hold it relatively tight. So just keep in mind, if you've got a round part, we're more than happy to help you with that as well. This is a material compatibility chart that we mentioned earlier that Catherine said you can download from our website. We also have some other really great resources on all welding technologies and maybe where they might fit as a rough guideline. We can go deeper, of course. Material types, we can help you out with this as well. Comparable material, you got to have compatible materials like we talked about. They don't have to be the same as we highlighted, but they have to be compatible. That transmissive and absorptive material, I think we've definitely pushed that. And then this is kind of an example of what I was talking about. That part on the left is the same part on the right. It's in our inspection system. You can see the rib. You can see a little bit of a flash around the whole thing, but that's the same part. And so you can get aesthetically a part that you would never know is transmissive to the spectrum of 1 micron. And we've talked about fillers quite a bit as well. I just want to make sure we save some time for this. We're talking technology. This was 43 minutes of technology. This is sort of the implementation spectrum that we see. Integrations, as we've talked about, we've executed those and have been able to have a really good solution. We've helped a company provide the weld joint design recommendations and verification. And then at the end of the day, we end up selling an integration package. We have a slick benchtop system. This is a little more than a lab machine, I would say. There are some benchtop systems out there that really aren't intended for production. This is really the best of both. We can get our costs down a bit. It's a little less material. It is a little less force and a little less footprint due to the height of the system, but as a really nice option. We've got standalone systems. This actually is a custom one, but we have inventory laser welders that are standard products for us. And then all the way up into the automated systems where we've got a standalone. That was a custom standalone, but this was a semi-automated, I would actually call it, where it had drawer slides and someone was inserting the parts. So those are just kind of the examples of the equipment that we use for that. If you are interested further, you can... do I have to say it?
Yeah. You got to say it.
You can say beam me up in the chat or submit a quote request on our website, of course. We'd love to schedule a discovery call, work with your design, stake, test parts, laser weld parts, offer recommendations, whatever you need. And then we'll decide on the equipment solution after we've got the technology sort of nailed down. So, yeah. Anything else to add there, Catherine?
Just that you don't have to pick one of these options on your own. I just really like to emphasize both picking the technology and designing your part, as well as configuring the technology within your floor space, your operator capacity, your line, this, that, the other thing. You don't have to make that decision on your own. We'd like to work with you to make sure that you're receiving the best plastic joining solution for your application. I always tell people no one wins if you end up with a paperweight in the end of this. So doing the work on the front end to figure out what you need and how we can achieve what you need, that's what we're here for. So type beam me up in the chat and we can start that conversation. I wanted to do it too. Yeah.
Beam me. I don't know how the actual beam me up from a show. Beam me up, Scott.
Yeah, Star Trek.
Yeah.
I've definitely seen
big trucker, but we know that given 45 minutes is a lot, we really appreciate it, and we're here to help.
We appreciate all the questions that you guys have asked along the way. If you have any other questions, you can ask them now. Otherwise, if you want, you can respond to the email that's going to go out to all of the attendees that has the recording, PDF of the slides. I'll send the compatibility chart and a copy of the design guidelines.
Would it be overwhelming to add one more thing to the email?
Not at all. I can write it down right now.
I feel like the decision matrix would be a very helpful.
Oh.
I mean, just so that they have it, just in case they're curious.
Okay. And anything else?
Maybe a GIF of sharks shooting laser beams out of their eyes or something. It would be.
I
good.
went with an office reference.
Yeah, I think a GIF of Dwight Schrute saying thank you is
Never
pretty good.
bad. Perfect. Thanks, everyone.
Thanks for joining. Have a great rest of your day.